First of all, I thank the organizers for the opportunity to talk at this wonderful conference. I have a disclaimer similar to the one from the previous speaker. I'm not a mathematician and even not quite a mathematical physicist. My talk is a talk from the point of view of a physicist who just uses integral models in order to get intuition about physics. So I will be grateful for any comments or criticism from your side. So please, you're welcome. I will talk about quantum dynamics in a many-body system. There are some fancy drawings on the right of the presentation. This is just to emphasize that this is not just an some fancy mathematics or fancy theoretical physics, but currently with the advent of quantum devices that can operate single bits coherently, integral Hamiltonians, or in fact many non-integrable Hamiltonians also can be realized in arrays of quantum dots or superconducting qubits or ultra-cold atoms in arrays of optical tweezers. And many of the questions we will be talking about can be actually addressed experimentally now or in the nearest future. So I will start from a very basic introduction, and please forgive me if it is too basic, still at least to introduce the notations. So we are studying dynamics of many-body system described, quantum many-body system described by Hamiltonian, and we are interested in the dynamics of the expectation value of some particular observable, which is described by a Schrödinger operator O. The system is initialized in some out of equilibrium state, described in general by a density matrix ρ0, and it evolves according to the von Neumann equation, which is a linear differential equation on the time-dependent density matrix ρt. So in principle, if we calculate ρt from this equation, we just plug it to this expression and calculate the expectation value of the observable at time t. In practice, however, this von Neumann equation is prohibitively complex in a general system. So a natural idea is to try to solve this equation for integral system and hopefully get some intuition. However, a bit ironically, even if the Hamiltonian is integrable, calculating the dynamics of an observable is usually a daunting task. The most straightforward approach is to use a form factor expansion. It is written here, so let's look at this formula. It has several ingredients, and it is a sum over eigenstates of our integral model, which we know from, say, Bethe ansatz or Jordan-Wigner transformation for free fermionic models. It is a double sum, so we have to calculate first diagonal and non-diagonal expectation values of our observable. Then we have to calculate the scalar product of our eigenstates with the initial state. Here I assume for simplicity the initial state is a pure state. Then we have to take the sum, the double sum, and also it is desirable to actually take the thermodynamic limit usually. So in practice, there are few works that manage to do this for some particular models. However, there are really few. So it's really each ingredient is really technically a technically complex task. There are other methods, say quench action approach, generalized hydrodynamics, and some others. However, each instance of a solved dynamical problem for integral model is a tour de force. An approach that I will present is really straightforward, and it's not new, of course, but for some reason it wasn't used a lot previously, and my message is that it is worth looking at and trying and attempting. The approach is to go to the Heisenberg picture and to try to solve a system of Heisenberg equations, as simple as it is. Let me briefly remind you this Heisenberg representation. So instead of calculating the time-dependent density matrix and then taking the trace with time-independent Schrödinger operator, we can use this cyclic property of the trace and to write the expectation value in this form, where this ρ0 is the initial density matrix, and this OT is the Heisenberg operator given by this equation. Sorry. So now all the time dependence is in the Heisenberg operator, and it evolves according to the Heisenberg equation that looks like. Technically, what we need to, how do we write down this Heisenberg equation? Technically, all is boiled down to taking a commutator. So the commutator of the Hamiltonian with the Heisenberg operator is the commutator of the Hamiltonian with the Schrödinger operator multiplied by the evolution operator. So in practice, taking time derivative of the operator is just equivalent to taking the commutator with the Hamiltonian. Just a brief remark that the Heisenberg operators are also useful for calculating correlation functions, not only the quench dynamics I'm talking here about. Now let's start from a very probably one of the simplest integral models, the transverse-field Ising model. For now, I will pretend that I know nothing about Onsager algebras and that the Hamiltonian is an element of Onsager algebra. I will just take the commutators one by one and see what happens. Here, let me simplify notations. Since the Hamiltonian is translation invariant, and I assume translation invariance here, periodic boundary conditions, and we wish to study a translation invariant operator, we can actually drop these sums and these indices. So, for example, the sum of this nearest neighbor interaction is written simply like this. The sum of this next to nearest interaction is written like this. Note this identity operator, which tells us that this is the next to nearest interaction. In these notations, the Hamiltonian is written simply. In this form, this A1 and A0 are simply numerical coefficients, and sigmas are Pauli matrices. Okay, so and we'll take the observable, which looks like XX nearest neighbor correlation. The first derivative of this A1 is just the commutator, and it looks like this. Now we need to take the derivatives of these operators, and I don't write down here the numerical coefficients, which are the polynomials of A0 and A1, but just the operators that enter this commutator. They look like this. Now we have to take the time derivative of these operators, and you see that, in fact, here you can already see the structure which emerges in these operators. So first of all the operators which emerge as strings, that is sequences of non-trivial operators acting on consecutive sides. This one commutator. So at the ends of these strings are either sigma x or sigma y. In the middle of these strings are only sigmas. Now we introduce two family of operators, Gn and An. So they are strings or linear combinations of strings. As I said, in the middle of the strings there are sigma z's, and the ends of the strings there are either sigma y's or sigma x. And we get a system of equations for this An and Gn. It looks quite simple. Note that although the full space of operators of an n spin of spin 1/2 model with n spins is 4 to power n. However, here we get not an exponential but a linear number of operators. It's linear in the number of spins. And of course, all of you can recognize a representation of the Onsager algebra here, but we pretend that we know nothing about the Onsager algebra. Now, these Heisenberg equations can be solved, and I will probably skip the technicalities and just show you the result. So the result looks as follows. The Heisenberg operator for Gn is a sum of Schrödinger operators, linear combination of Schrödinger operators Gm, Am, A minus M, with time-dependent coefficients. So on the left-hand side, we have a Heisenberg operator which is which we wanted to find, and we find it as a linear combination of Schrödinger operators, which we know how they look explicitly, and just some C numbers functions of t. And of course, we can get an expression for A of t, but it just simply quite bulky. Now, when we know an explicit form of the Heisenberg operator, we wish to explore dynamics after some particular quench. That is, after preparing and initializing the system in some particular initial state. As an example, we take this initial state, which is a state of uncorrelated polarized states, spins with the polarization p. So we have to insert this rho 0 into this trace, calculate the trace of each of Gm and Am with rho 0. It can be done easily, and you get expressions for the expectation values of these operators, An of t, Gn of t, actually in a bulky but elementary form. And here you see some plots. This is the magnetization along the z direction, and this is correlation, nearest neighbor correlation as functions of t for various values of parameters. So we get this explicitly. This is the initial polarization. Of course, we know that transverse-field Ising model is equivalent to non-interacting fermions. Here I briefly sketch the map between the spin representation and the free fermionic representation of the model. The result of this map is this quadratic in fermionic, quadratic Hamiltonian, quadratic in fermionic operators. It can be easily seen that An and Gn are also quadratic in fermionic operators. So one might think that all the story I have told you is simply trivial, because an evolution of quadratic operators under the Hamiltonian dynamics induced by quadratic Hamiltonian is somewhat trivial. In fact, this is not quite the case for the following reason. Initial states that look simple and natural in the spin representation, not necessarily simple and natural in fermionic representation. For example, this simple uncorrelated initial state for polarization. This is actually a pure state because I take polarization vector equal to 1. In the fermionic representation, looks something like this. So you take the fermionic vacuum, which is say all spins down, and you should act by two exponentials on it, and what you get is a superposition of states with all possible fermion numbers. This means that if you wish to solve your problem for this initial state through fermionic representation, you actually need to solve n plus 1, maybe, and okay, n different fermionic problems with different fermionic numbers, then sum up the amplitudes, and then somehow get the answer. This is in principle possible, but I have never seen any paper where this were done in practice. In our approach, this initial state poses no difficulties at all. Now let's come to the Onsager structure of the Onsager algebra. It was already discussed in this conference several times, so we just cite it one more time. The algebra can be generalized from A0 and A1 recursively through these relations, and the condition when A0 and A1 actually generate the Onsager algebra are Dolan-Grade conditions. So the Ising model is one representation of this. The Hamiltonian of the Ising model is written in one representation of the algebra. However, an important result obtained long ago by Kitaev and Heisenberg is that for each small n greater than or equal to 1, a spin n divided by 2 representation exists with nearest neighbor Hamiltonian. The Hamiltonian looks in terms of these generators A0 and A1 exactly as the Ising Hamiltonian. For spin 1/2, this is a transverse-field Ising model. For higher spins, this is a superintegrable chiral and state-force model. Models that also have been mentioned and discussed in previous talks. In contrast to the Ising model, however, the n-state-force model, as far as I understand, cannot be mapped to free fermions. However, I'm embarrassed to say that I came across these papers by Minami, a series of papers by Minami after I made this work and published it. They discussed generalized Wigner transformation for these chiral and state-force models. So actually, I'm not even sure that they are not related to some fermionic models, at least in some sectors. But this is probably my ignorance, not the question, the over question. What is good with the Onsager algebra is that as long as we have got the answer for the Schrödinger operator, it is valid for any representation, because the von Neumann equation amounts to just taking the commutators, and the result of the commutation is determined by the structure of the Onsager algebra and not by the representation. This means that our result for the Heisenberg operator is valid for all n-state-force models that are presumably not equivalent to free fermionic models. But there are important differences yet with the Ising model, and let me show you an example of the simplest chiral ports model, the three-state ports model. It is A0 and A1 look like this, where this is spin 1 model. The single side operators tau and sigma can be written in some ways. And the defining algebraic relations for them are written here. This number W is just the definitions, and the Hamiltonian, sorry, I haven't written it, but the Hamiltonian is again a linear combination of A0 and A1. Here is our answer for the Heisenberg operator. However, in contrast to the Ising model, general formula for AN and GN are unknown. So we can generate them recursively, one by one, using a computer algebra code from the defining relations. For example, G1 looks like this. And actually, the complexity of higher G's and A's grows very rapidly. Here in the table, you see the number of non-trivial terms in AN for different n's, and you see that even for n equal to 4, it is almost 200. In general, I do not see any apparent structure in this AN and GN. Certain properties can be guessed, however, from these computer algebra simulations, and they will be important for calculating the traces which are required for getting the answer for the dynamics. The complete set of single-site operators contains 9 operators for spin 1, and we take it as follows. And it is divided in two subsets: non-shifting operators and shifting operators. And the terminology stems from the fact that these non-shifting operators do not change the sigma z projection of the spin, and these ones shifted they shifted by 1 in a cyclic way. Here are some conjectured properties of AN and GN. Probably I don't have time to discuss them in detail. Just I will show you a single term entering A4. So it looks like this, and you may check that all these properties are indeed satisfied. So the properties have been checked for n up to 8 by performing direct calculations. And these properties, actually, I don't show it, but these properties are instrumental for calculating the traces or the initial state with this AN and GN. Since we do not know the all AN and GN, we have to truncate this sum at some m. However, it turns out that the sum converges rapidly, and we get a pretty exact answer already for n equal to 6. So this is the result for magnetization on the z-axis, and these are some estimates of the accuracy, and the accuracy grows exponentially with the truncation, the number of. Now I have less than 5 minutes, and let me briefly sketch the open problems. The first one, as I have said, there are no explicit formula for n-stage representations of Onsager algebra. They are highly desirable, or at least the proof of their properties is desirable. Then one can hope to study not just translation invariant operators, but site-resolved dynamics. This is straightforward for the Ising model, but probably not that interesting. For higher spins, one needs to generalize Onsager algebra in a site-resolved manner. And I do not know whether this is possible, and whether, so I don't, the paper by Uglov and Ivanov attempted this, but they managed this only for the Ising model, and I actually don't know whether this is possible for post models. Well, other open problems include, well, in principle, one can hope to find non-local presentations of Onsager algebra, quasi-local, not just nearest neighbor. One can try to tackle time-dependent Hamiltonians, and one can try to tackle in this way open systems. Now, I have 2 minutes as far as I can see. Am I right? Okay. Then
yeah, you have 2 minutes.
Yeah. In the title of my talk, there were models with Onsager algebra and more. And in these 2 minutes, I'll tell you about this more. This more is actually a Kitaev model on a honeycomb lattice. It turns out that you can actually push the same approach to apply it to the Kitaev model on a honeycomb lattice, but not actually on a honeycomb lattice, but on a Bethe lattice, which is honeycomb-like. This Bethe lattice is different from the honeycomb in the sense that it has no closed loops. I will skip the technicalities. The main point is again that we get strings here, and we write down quite scary equations on these strings, and although they are scary, they can be solved, and we solve them and get the result. And here is red curve is our result, and blue curve is the result of a numerical calculation on a true honeycomb lattice. They are quite close, which is physically, which can be physically understood. So let me skip this discussion of the difference between the honeycomb lattice and the honeycomb-like Bethe lattice. Let me skip open problems and let me just finalize the talk by the main question which emerges here. Are there any other non-trivial models that can be addressed by this method? So for now, this method has been applied either for models that are equivalent to free fermions, that is Ising model or Kitaev model on a honeycomb-like lattice, or to the n-state pods models which have this Onsager symmetry and allow for generalized Jordan-Wien transformations. However, it should be noted that actually to have an algebra, to have a Hamiltonian as an element of an algebra is redundant for the method. What one really uses is the closeness of the set of operators with respect to commutation with Hamiltonian alone. So maybe other models can be solved by this method, although they don't have such profound algebraic structures as the Onsager algebra. So that's all. Thank you for your attention, and sorry for being late for a couple of minutes.
Thank you. I have a question about the inverse problem. So do you know if it's known the precise relation between for instance, the Pauli matrices at site, let's say I, in terms of Onsager generators?
I don't think, if I understand correctly the question, the Onsager generators are translation variant operators that are just the sum of local terms over the whole lattice. Now there is a question of generalization of this algebra to in a site-resolved manner. So of course in the transverse, let me show you the Hamiltonian. So a set of all individual terms like this and this also generate an algebra, which is larger than Onsager algebra, but still it is an algebra, and one can push this method using this large algebra. There is no questions about it. However, I do not know whether this works for less trivial, less simple n-state pods models. I don't know whether this answers the question.
Other questions, remarks, comments? Let's take the speaker again.